Hi, myself Prithviraj. Today we are going to discuss about one of the important algorithm that comes under module 3, that is Prim's algorithm. Prim's algorithm is one of the efficient algorithm that is used to find the minimum cost spanning tree. First of all, we'll see what you mean by spanning tree. Spanning tree is a tree, or like it's a subgraph of a connected graph G, which has all the vertices which are there in the main graph, but it should not form any cycles in it. Minimum spanning tree is a spanning tree with the smallest weight. Any spanning tree which has very less number of weight is called as a minimum cost spanning tree or minimum spanning tree. Now, the minimum spanning tree problem is a problem of finding minimum spanning tree for a given weighted graph or weighted connected graph. If you want to find out the minimum cost spanning tree, you may have to follow some of the algorithms. So in order to identify the minimum cost spanning tree is called as a spanning tree problem. In this example, we can see a first diagram that indicates the main graph, and the remaining three diagrams that is used to indicate the different spanning trees. We can achieve three number of spanning trees from the main graph, and in the second diagram we can see that the weight of the spanning tree is 6. In third diagram, weight of the spanning tree is 9, and in last diagram, weight of the spanning tree is 8. Now compared to these three different diagrams, uh, second one, that is weight 6, is the minimum weight. Hence, this spanning tree is called as a minimum cost spanning tree. I hope you got a clear picture about the minimum cost spanning tree. Now, let us discuss about the Prim's algorithm. Prim's algorithm constructs a minimum cost spanning tree through a sequence of expanding subtrees. The initial subtree in such a sequence consists of single vertex selected arbitrarily from a set of vertices. Initially, we have to consider one vertex as the starting vertex or the initial vertex. On every iteration, the algorithm expands the current tree in a greedy manner by attaching to its nearest vertex. So, while solving the problem, we'll come to know each time we have to attach the nearest vertex to it, and the algorithm stops after all the graph's vertices have been included in the tree that has been constructed. So these are all the different steps that we need to be that we need to follow while solving the problem. Let us consider one simple example. This is the given graph. Now for this graph we have to uh, identify the minimum cost spanning tree using Prim's algorithm or Prim's method. Uh, Let us begin with the problem. We'll take two columns. One is the tree vertices and second column is the remaining vertices. Initially, we will take one vertex as the smallest, initial vertex. Uh, Let us take the vertex A and dash comma dash. That means it indicates a weight. Now, we doesn't know what is the weight. Initially, we will take the vertex, and the remaining vertices are, one is B, and we have to see whether there is a direct edge from A to B. Yes, there is a direct edge from A to B with the weight 1. So we need to write it as B of A comma 1. Next vertex is C, but there is no direct connection from A to C. Okay, so that we have to write it as C of, from A the weight is infinity. That means we doesn't know the exact weight. Okay, then another vertex D. from A to D, we know that there is a direct edge with the weight 3. Next, E, again from the diagram, from the figure, we can see that from A to E, we don't have direct path or direct edge. So we will write it as E of A comma infinity. I hope the first row is clear to everyone. Next, from these remaining vertices, we have to choose a vertex or an edge such that the cost should be minimum. So by looking at the number of remaining vertices, we can say that B of A comma 1 is the minimum weight among all, because another weight is infinity, 3 and infinity. So we will take the next 3 vertices as B. Now here we have taken one entire edge. We can see the entire edge from A to B with the weight 1, so that we can take the edge from A to B with the weight 1. Now by keeping B as a reference, write down all remaining vertices. From B to C, we have direct path from B to C, and look at the previous step. C, in the remaining vertices, C of A comma infinity we had. Now here we are writing C of B comma phi. Now here again we need to compare whether phi is smaller than infinity or not. Okay, now phi is smaller than infinity, then we can take this as the new vertex with the new weight, that is C of B comma phi, since we had direct path from B to C. Next, from B to D, we have B to D. Actually we don't have the direct path from B to D, but in the previous step we had A to D as 3, cost was 3, so that we can, instead of taking infinity, we can directly take D of A comma 3. Next, from B to E, again we don't have direct path, direct connection. So as in the previous step, again we had E of A comma infinity. So let us write down the same thing, E of A comma infinity. Either you can write E of A comma infinity or E of B comma infinity. Okay, that doesn't matter, because both infinity and infinity are same. Okay, so these are all the remaining vertices. Now when comparing with all the vertices, I mean all the weights of those edges, we can see D of A comma 3, because 3 is the minimum weight, so that we'll consider the next next vertex as D. That is, we have taken the edge A to D. So we have considered the edge from A to D, and what is the weight? That is 3. Now by keeping D as a reference, write down all remaining vertices from D. Now, first one, D to C. Now you can see that in the previous step C of B comma 5 was there. Now here from D to C we have direct edge with the weight as 4. Now instead of writing C of B comma 5, we can write it as C of D comma 4, because 4 is smaller when compared with 5. Okay, so that we have taken C of D comma 4. Next vertex is E of D comma 7. Now we can see in the previous step we had E of A comma infinity. Now compare 7 with the infinity. So 7 is a smaller one, then we have taken E of D comma 7. Then is there any other vertices left? No, only 2 vertices from D. Remaining all vertices are already over. Now comparing these with these two, C of D comma 4 is a minimum, because 4 is a minimum weight, then we can take this as a next vertex. So we have taken the edge from D to C with the weight 4. Okay. Now from C we have to identify the remaining vertices. Now from C we have direct edge with the weight as 8. Just look at the figure. From C to E we have direct connection, direct edge with the weight 8. Now is it okay if I write E of C comma 8? Because in the previous step we have E of D comma 7. So compare two weights 7 and 8. 7 is the smallest one, so that we can take it as E of D comma 7. Okay, only one vertex is one vertex remaining, so that in this E of D comma 7 itself is the smallest one, so that we can take it as a next vertex. Is there any vertices pending? No, there is no vertices remaining. Now lastly we have taken the edge D to E with the cost as 7. Okay, now this is the minimum cost spanning tree, so that we can see in the diagram there is no cycles formed. We should not form any cycles in a spanning tree. So with this, minimum cost spanning tree is 1 plus 3 plus 4 plus 7. So total cost would be 15. So this is how we can find the minimum cost spanning tree using Prim's algorithm. And this is the exercise problem for you. Go through this figure and calculate the minimum cost spanning tree using Prim's algorithm. Thank you.